Everyone. In this occasion, I'm going to explain to you an interesting article entitled Plastic Black Lab on a Chip for Fluorescence Excitation with Integrated Organic Semiconductor Lasers. Well, first, it's important to mention here that laser light excitations or fluorescence markers offers high sensitivity and specific analysis for biomedical and chemical analysis. And so here it's important also to know that this optical analysis is the most promising because first, high sensitivity and also short response time. So here the authors designed a lab on a chip, so a microfluidic device with integrated organic semiconductors, lasers, and in combination with passive photonic components and also in these microfluidic structures. So here to make it simple, they integrate an organic semiconductor called trace aluminum doped with a laser dye. And finally, and also with deep ultraviolet induced wavelengths and a nanostructure. All of these were integrated in a nanostructure microfluidic channel in PMMA substrate. It means a chip of polymethylate. So the methodology they use here to perform this setup at first, it was, as you can see here, here is the laser, the waveguide, and also the fluidic channel in the PMMA substrate. So, to synthesize the steps they follow to perform this experiment, at first they did thermal imprinting, then did UV exposure, and the another step was evaporation of the laser material by thermal bonding. Finally, was then the excitation of the fluorescence marker in order to test this micro device. And while they use two model system labeled with antibodies with light emitted. So at first, and then the experimental setup they used to see what was happening, sorry. It was a UV laser emitting pulses of less than 5 nanoseconds at this wavelength 349 nanometers. And also they use a beam splitter and a calibrated photodiode. Also to control the position and the size of the chip, they use a camera. And also they use two different long pass filters in order to avoid the laser light and to block the laser light and only exceeded the fluorescent light to be detected. As you can see here in this figure. So then to prove the functional capability of the device, they excite fluorescence markers in aqueous solution microfluidic channels. They were filled with the first carboxylate modified microspheres that let's call them fluorospheres, and the other was the blood anti-mouse immunoglobulin G antibodies labeled with Alexafluor. And those solutions were used to test if the chip could be seen with this fluorescence material. So the results, as you can see here in this image, in this picture, it can be demonstrated the fluorescence excitation. So the laser line is clearly visible on the top of the fluorescence of this material in the fluorosphere. Also, as you can see here in this graphic that describes the wavelength in terms of intensity, we can see that the features were correctly applied. And with this image, it is characterized that the fluorescence were seen in the correct with the correct spectrum. So the conclusion is that this setup enables the excitation of the fluorescence markers, which are utilized as labels for both microsphere and also for antibodies. And so the next investigations here is to include the time, the time dependent analysis, and also create more, trying to functionalize the interaction zone in order to enable a specific detection of multiple analyzed components. So here we're demonstrating fluorescence that could be seen even on those PMMA substrate. This also thanks for the optical, optometric, electronic devices setup. Thank you.